Okay, welcome back to what should hopefully be the last video in Chapter 6, and it involves friction. It is this last type of problem we're going to look at is a problem in which we have a box on a horizontal surface. We apply a horizontal load to it, or in this case, two loads, and what we want to know is what's going to happen to this box. Is it going to slide along the surface, or will it potentially tip over? If it were to tip, it would tip about this point. This would be the point of rotation about which tipping would occur. So basically, what we need to do is consider the center of gravity of this box. And so its weight is acting at the center of gravity. And look at, first of all, how much force is going to be required to tip it over. And then we need to look at, how much force is required to make it slide. And then we need to sum the moments about this point to see how much force is required to tip it over. And then see which of those two things is going to occur. So I guess we'll actually first look at the force required to cause this box to tip. So if it's going to tip over, it's going to tip over about point A. That's the point of rotation. So this 100-pound force that's applied, it has a moment arm distance of 5'6" or 5.5 pounds. The box has a width of 4.5 feet. So the moment arm distance to the center of gravity of this box is going to be half of its width. So it's going to be 2.25 feet. And then we have an additional pulling force with a 5-foot moment arm distance. So what would the force P be that would cause this to tip? The impending motion of tipping would occur when all of these moments are at a state of static equilibrium. If they were at a state of static equilibrium, then we would know what the, essentially, in this case, literally, the tipping point is that is going to cause any additional load P is going to cause this thing to tip over. So let's sum the moments about point A. They include the 100-pound force, which is going to be multiplied by its moment arm distance of 5.5. It's going to cause clockwise rotation, and that is negative according to our sign convention. Next, we have the 450-pound weight of the box itself. It has a moment arm distance of 2.25 feet. It is going to go in the opposite direction. It is going to cause counterclockwise or positive rotation. And then finally, we have our pulling force P. It's going in the negative clockwise direction, and it has a moment arm distance of 5. And all of that will equal 0. It's all going to cancel out due to static equilibrium. So what is that pulling force? It is going to be equal to 450 times 2.25. 25, let's fix that. There we go. 450 times 2.25 minus 100 times 5.5, and then divide all of that by 5. Let's see what that's equal to. 92.5 pounds. So if we pull on this crate with a force of 92.5 pounds or more, we'd actually need to pull slightly more than that, then we're going to cause this to tip over. The moments about this point are going to be such that there is an imbalance of forces and motion will be impending. Now let's calculate the force that would be required to cause this box to slide across the ground. So to calculate that, instead of summing moments, we're going to sum the forces in the x direction and figure out the point at which it's in a state of static equilibrium. So we're going to find the force P that doesn't necessarily cause it to slide, but it's the point at which any additional force in that x direction will cause sliding. It's going to cause force to be or motion to be impending. And so those forces are going to include the 100-pound force that's being applied right here, and P, which we don't know yet, and F, which is going to be going in the opposite direction of motion. And we don't know that yet, but we can calculate that. The friction force is equal to the normal force times the coefficient of friction. There are no externally applied forces in this problem in the vertical direction other than the weight of the box itself. And so that's going to be acting down. So the normal force that's pushing back against it is just going to be 450. That's going to be the normal force. So we're going to have 450 pounds of normal force times our coefficient of friction of the problem statement said that was going to be 0.4. So that is equal to 180 pounds. So this equation back here becomes 0 equals 100 plus P minus 180. So we solve for P. We can see that P is equal to 180 minus 100, which equals 80. So it takes 80 pounds to slide, and we calculated earlier that it takes 92.5 pounds to tip it over. So that's 92.5 pounds to tip. So if we started pulling on this crate and we gradually increased the force with which we pull, we're going to hit 80 pounds of force before we hit 92.5 pounds. So it is going to start to slide first. It requires less force to slide, so that is what is going to happen. It is going to start to slide. So it isn't going to tip. It is going to slide. So that's the answer. The answer is slide, and the force that's going to be required to make that happen is 80 pounds. And I believe that's it. That's the last type of problem we're going to see in this chapter, chapter 6. So we've looked at pushing or sliding a box across a horizontal plane, the force required to push a box up an inclined plane or prevent it from sliding down an inclined plane. We've looked at the belt friction of wrapping a belt or rope around a static drum. And now we've looked at this situation, which is sort of like the first type of problem we looked at, sliding a box across a horizontal surface, but we've also included the possibility of tipping the box over. So if we think about this problem, if it had come up the other way, if we found that applying our forces is going to cause the box to tip over, and we don't want that to happen, the way we can fix that is by lowering the location of our force. By reducing the moment arm, that's going to increase the likelihood of sliding occurring rather than tipping. If we were to raise these moment arms, if this 100-pound force and force P were applied higher up the sides of the box, then it would be more likely to cause tipping. But in this case, with these moment arms and these forces, it will slide. And yeah, that's it. That's it for chapter 6. So as always, if you have any questions, please utilize the discussion board on Blackboard so that your classmates can benefit from those answers, or come to class prepared with questions to ask, and I'd be happy to answer those questions.